Okay, good afternoon to everyone on the line. Welcome to today's webinar presented by Makino. I'm your moderator, Kara Dacknodle with Mold Making Technology, and I'm thrilled to be a part of another hot topic webinar by the experts at Makino. We appreciate you taking the time to be with us today. Today's webinar is the benefits of 5-axis machining in the die mold market. During this webinar, we will learn how 5-axis machining techniques can cut your machine cycle time, reduce perishable tooling costs, and minimize tedious polishing time as well. Today's presenter is Bill Howard. He is a product line manager for vertical machining centers at Makino. He holds degrees from Penn State University and the University of Cincinnati in mechanical engineering, and holds an MBA from Xavier University. He has 48 years of experience with machine tools and capital equipment. Bill is also an associate member of the American Society of Mechanical Engineers and a senior member of the Society of Manufacturing Engineers. Now, before I pass this on to Bill, I want to let you know that you can ask questions during the presentation by typing them into the questions panel on your computer. Then at the end of the presentation, Bill will try to answer each one. And as one last reminder, this webinar is being recorded, so you can watch it later online if you want. Bill, take it away.
Okay, thank you very much. On behalf of Makino and myself, I'd like to thank Mold Making Technology for this opportunity, Gardner Publications. So as you can see, benefits of 5-axis machining in the die mold market. Just for reference, if I guess folks aren't as old as I am, but this is the way we used to make parts for die mold, and it was 3 axes. And you can see we just keep stepping down and pick feeding down in Z using X, Y, and Z. Well, obviously that things have changed. And today we can literally with 5-axis technology move the part relative to the spindle. And that's what you'll see here. So this happens to be a D500 machine from Makino, but very, moving, tilting, and rotating so that we're positioning the part relative to the spindle. Or the other opportunity you have here now is to use or articulate the spindle relative to the part. So when obviously this part's a lot larger, it's going to be heavier. So you get into inertial and speed kind of impact. So here you can see now we can position the spindle in the tool relative to the part. In either event, those are now 5-axis approaches to die mold. And so what are the advantages? And here's one right away. In the past, tool, you were cutting at the null point, if you see down there at the bottom. So it's really not the ideal point. So you ended up with relatively lower feed rates and a non-homogeneous surface finish or roughness. And really with the technology, the 3-axis, there was not much you could do. Today, now we can either tilt the workpiece or tilt the spindle so that we can literally get an optimal contact between the tool and the workpiece. So we can get selectable velocity there. We can cut with different sides of the tool or different flutes, if you will. We can get higher feed rates. So we end up getting much better surface finish and a consistent surface roughness or finish there. What are the advantages? Obviously, much better cutting conditions because we're not cutting with that null or end point of the tool, and obviously not cutting with the end point of the tool. That's going to generate better surface finishes. It's going to reduce or eliminate. That's one of the whole objectives here, is to get the workpiece off of the machine in a much better shape and condition, much better surface finish, so we can get rid of, reduce, or totally eliminate the hand finishing and secondary operations after you take it off the machine, which obviously increases cost and increases your lead time and turnaround. Sorry. I apologize. I hit the wrong button. I'm going to flip back up through this. Please excuse me. I didn't mean to do that, but this does give you a real quick preview of what we're going to see. Find where I was. Here we go. I will make sure I don't do that again. Better surface finish to reduce or eliminate hand finishing. And consequently, now we can get multiple inserts or multiple cutting edges of that tool, so we can get longer tool life and therefore reduce cost. Now, utilizing shorter tooling is another key advantage. Again, in the past, if you were going down into that slanted or tapered surface there, you can see in order to get all the way down that side, you're looking at a 300 millimeter or almost 12-inch tool to get down in there. Well, now what we can do is we can either tilt and rotate the part, or in this particular case I'm showing, we're rotating the spindle, tilt and rotating the spindle. So you notice we've gone from L equals 300 or 12 inches down to L equal 150 or 6 inches. So we've gone with literally half the tool length. Okay, so that's a much shorter tool. What are the advantages of doing that? Well, obviously, the shorter tool length, you're going to be stiffer, more rigid tooling. That's going to reduce tool deformation and give you better cutting conditions. In addition, you're going to have less run out of the tool at the cutting edge, so therefore more accurate, again, better surface finish. It also allows you to run a much higher RPM because you don't have to worry about the run out, stiffer, more rigid. So faster speeds, increase your feed rates, less vibration, and better surface finish. You're going to end up with quicker cycle times, which is going to allow you to cut your lead time for manufacturing down. Much better surface finishes, which we've already talked about. You're going to reduce or eliminate hand finishing at the end, and you're going to get better tool life because of optimum cutting conditions, optimum contact, and stiffer, more rigid, less run out of the tool. That's going to reduce your costs as well. The other thing it allows us to do is use advanced tooling technology. You'll notice here a lot in the past we've used 2-flute ball nosed end mill. Well, this is a 6-flute ball nosed end mill. And the reason for this is, again, we can tilt the spindle or move the workpiece so that we can utilize multiple surfaces, multi-fluted tools on the machine. So that allows you to have much more cutting surfaces so the tooling can last longer. You can have more surface on a given tool. Also allows you to have much higher RPMs and much higher feed rate. So therefore, cutting your cycle time and longer tool life because now you have more cutting edges, cutting surfaces on that tool. And again, we've got optimum contact between the tool and the workpiece. So you're going to have higher productivity and again, maintaining much better surface finishes, all at a much lower cost. Another thing to think about is some of these advanced tooling techniques that have come along. Um, you'll hear me talk about barrel shaped tools. I think the technical name, the real technical name, is circle segment tooling. Um, Basically, now you can have a larger diameter and a smaller diameter on the same tool. Well, you might say, well, why would you want to do that? Well, you can get tighter surface finishes with fewer steps by indiscriminately using the larger diameter and then working down and using the smaller end diameters on blends and matches into the corners, things like that. So you can use on larger surfaces and tighter in corners. It also allows you, again, to run much higher RPMs and much higher feed rates. So you can machine in the past, if you think about it, you would machine a bunch of surfaces and kind of knit or stitch them together, blending them and matching. Now you can literally use one tool to come down across and get away from having to blend surfaces as one continuous surface versus blending surfaces. Um, Barrel shape tools, typically you're going to have very long tool life, much better, higher productivity, better surfacing. And again, there's multiple cutting surfaces. And the whole objective and goal here is to reduce or eliminate hand finishing at the end of this process, which is going to help your lead time. It's going to lower your costs. Now, this is an example of a circle segment or a barrel shaped tool. And what we're doing is we're pick feeding down a sloped surface. And you'll notice this happens to be on a 3-axis machine tool. So here's a benefit that you could even pick up. So you're going to see, because of the shape of the tool, we can get a much deeper pick feed and therefore a much higher feed rate. And you'll see how fast that we can machine that surface and get a very, you see where we've roughed it. Now we're getting into the finishing, very quick machining cycle time and a very good surface finish. Now, traditionally, and let me get rid of this. Sorry, for some reason, I've got, maybe it's the pollen in the air, but CAM systems have traditionally been one of the problems, and that's supporting 5-axis and supporting some of this advanced tooling technology, particularly as you get into the circle segment and the barrel type tool. That was one of the bottlenecks in the process. To enhance 5-axis capability, obviously you need to be able to generate the programs, the tool path, and to utilize the tooling technology. So today, with the advances and the evolutions, it's easier now to generate tool path and to evaluate tool path and also to support evolving tooling technology such as the circle segment and barrel tools. Multi-flute end mills, I didn't even mention that. So we need the capability to address those as well. Here's an example, and this is showing some of the advances. This is a CAM system, and you're gonna see this part later, but we're creating the program here for what we call the honeycomb, a honeycomb part. And you'll notice that we're programming this as if it were a traditional 3-axis part. So if you look at the tool and the tool path and everything there, it's a traditional 3-axis. So that makes it fairly easy to program. With the advances of and enhancements of the CAM systems today, you'll notice now you can go in and you'll notice where the arrow is pointing there. You can actually say to the tool axis, okay, I want to tilt the tool axis relative to the part. So that allows you now to literally take a program created for a 3-axis machine and utilize it in 5-axis. You can see here the tilt method. We want to lead. So that's what it's talking about here. So now we've literally changed the engagement, if you will, of the tool to the workpiece. And that's the whole point of 5-axis, is be able to change that engagement so that we're getting the optimum contact between the tool and the workpiece. Advantages for tool life, for surface finish, all of that. Same thing with advanced tooling support. Here's an example from a current CAM system where we're going in and supporting circle segment or barrel CAM type tools. And you'll notice there, this is another part we're going to see here shortly. This is a mold lifter part. And you can see how we're using a barrel segment or a circle segment tool, and we're going to do the periphery around the part, and we're using that circle segment of the tool to get a deeper pick feed so we can speed up the spindle and basically shorten the processing time of the part, but yet maintaining outstanding surface finish. So in order to support 5XC, which is 5-axis continuous, some of the advantages now with the CAM system is we can reduce the number of tool paths. So you don't have to have all these different surfaces that you're going to try and knit or stitch together, and then all the blends down in the radii and everything down in between them. So you can reduce the number of tool paths by doing 5-axis continuous. You can reduce the blending, matching, and stitching of shapes. You can also have support for collision safeguard. That's, you're building these models. We can import this kind of a Makino-esque, and I kind of apologize for, but we can bring those models in and actually use them in the background of the machine, a model of the part, model of the fixture, model of the tooling, and use real live data in the machine to prevent collisions on the machine while it's actually running. We actually are running ahead to make sure that there's no issues or problems. So that talks about Vericut in this particular case, and using those models that you've generated for the workpiece, the fixture, the tooling, all of that, importing that in. And there is a very simple plug and play window there that allows you to import those models. So now actually on the machine tool, you'll be running in background ahead of the actual cutting. So if there was an oopsie or a mistake somewhere, it will be caught before there's an actual collision on the machine. So collision safeguard protects your machine, your tools, your workpiece, all of that. What are the benefits of 5-axis? Well, significantly reduced cycle time because of less setups, less handlings. Also, increased throughput and reduce lead times because of optimum contact angle between the tool and the workpiece, which allows you to run higher speeds, higher feeds. Also, less run out, more stiffness and rigidity supports that. So you're much higher productivity. You can improve your access to part geometries, whether that be shorter, stiffer tools, getting down into corners of workpieces. Again, reduce the number of tool paths, reduce the programming time, more uniform surface finishing quality. One thing about it, when you can uniformly position the tool the way you want it on the workpiece, that allows you to get a uniform surface finish and uniform quality across the workpiece. It's going to benefit you. You've got multiple cutting edges. You can get the tool in the right position relative to the workpiece. So you're going to have longer tool cutting life. Again, better blending and matching. Part of that is multi-insert. Part of that is the circle segment type tooling. Ultimately, what we want to do is finish the part on the machine and get rid of or reduce all the hand finishing that has to occur after the process and taking it off the machine. This is kind of interesting here, and we'll show this. It says use less expensive tooling. And you're probably sitting out there saying, well, Bill, you're talking about all this circle segment tooling and six cutting edges. That doesn't sound less expensive. We'll show you in a minute how it works out to be less expensive. And all of this allows you to lower your costs and increase your profitability as a die mold manufacturer. 5-axis continuous. So we started out at the very beginning with that little video showing you how traditionally 3-axis is how we cut parts. And then we started going to a tilt rotary table, and we would do 2+3, where you'd basically position and lock your two least accurate axes and machine with X, Y, and Z. So 2+3 in order to, again, shorten the tooling. Look at the difference in tool length there. And now we're to 5XC, where 5-axis continuous. You literally can move either the part to the tool or the tool to the part. You have some examples. I mean, this is all good, fine, and dandy, but what about examples? We're going to share with you two different parts. One's we talked earlier about a honeycomb. It's actually an electrode. It's a honeycomb graphite. Looks like that. And then we're going to share a mold lifter. And there's actually two cuts on that mold lifter. One is around the periphery and one is on the top surface. Again, excuse me, I'm just trying to keep from coughing here. We'll go with the honeycomb first. This is actually on a D200Z machine. You can see the graphite electrode in there. And we're actually doing 5XC machining. So you'll notice, and you can see some, if you're familiar with some TCP tool center point control, we're working down the sidewall. We saw the programming there earlier. We're working down the sidewalls and then actually going down into the corner at the bottom and matching the bottom or in one continuous cut, finishing the bottom and moving right up into the side walls. Well, let's take a look at a 3-axis approach and a 5-axis approach. First thing you'll notice, cycle time. We went from about almost 5 minutes to just slightly over 4 minutes. So there's a reduction there of, I'm sorry, that's hours, almost 5 hours to slightly over 4 hours. So there's an over 18% reduction just in cycle time. And we looked at tools. Well, the 4-axis approach uses 4 tools versus I'm sorry, uses 3 versus 4 in the 3-axis approach. So you have less dollars in tooling. The tooling costs, if you actually look at those, you're looking at $60 versus $23.50. So a 61% reduction. And your lead time, obviously, you've got less cycle time, um, less machining costs. And we just figured this at $100 an hour. You're looking at $500 a part versus $400 a part. So 18.1% reduction. Part cost, if I take 3-axis, and in part cost, I evaluated here at $100 an hour. So I've got the cycle time and then I've got the tooling costs. So I'm looking here at about $556 versus $430. So about $126, $130, or a 22% reduction in the total part cost for that particular part. Now let's look at the lifter. Now this is a little different. First off is around the periphery of the part. So what I've got here is some video of the application. First off, you're going to see we're cutting with a 2-flute ball nose end mill, 1500 millimeters a minute, and a pick of 0.15. So that's what we're doing. We're working around the periphery of that part. And there you can see the 2-flute end mill there in the picture in the background. 59 minutes. Now we're going to take a 6-flute ball nose end mill, and notice what we've done. 3 times the feed rate, 4,500 versus 1,500. Pick feed's the same. Well, we went to 26 minutes. And then last, we're going to use a barrel tool, twice the feed rate, 3,000 versus 1,500, and 3 times the pick feed. We've went from 0.15 to 0.45. Now, what does that mean? Well, if we started out, we had 59 minutes, and then we cut that to 26 minutes by going to basically the 6-flute, and which allowed us to triple the feed rates. So we dropped the cycle time by 33 minutes, which is almost 56%. But then that last step, we dropped out another 13 minutes or 52% more. So if you look from start to finish, we dropped out 46 minutes, which is almost a 78% reduction in machining the periphery of that mold lifter. So that gives you an idea there. That's pretty impressive, 78%. Now, what does that mean on cost per part? I just went in here and ran it at $50 an hour, $100 an hour, and $150 an hour. So, I mean, take 100. The part price went from $100, 98.34, to 21.67. So significant drop in the cycle time on the machine times the cost per hour. Another interesting thing is tooling costs. There's the 2-flute, there's the 6-flute, and there's the advanced tool, the circle segment and barrel tool. So you'll notice we're actually spending more for tooling. So you'd think that you're going to spend more on the part. Well, the tool life we had for 3 hours there on the 2-flute, and I'm sorry, 3 hours. What we did was we just carried 3 hours all the way through. We held that variable constant, even though we know when we go from 2-flute to 6-flute, there's going to be much more cycle time, tool life. And when we go from the 6-flute to the barrel segment tool, we know again there's going to be much longer tool life. So we're not including in this calculation any of the benefits, and that's why it's in yellow there, of expanded tool life or extended tool life. So if you work this out, you can see it's $50 a part to $30 a part to $20 a part. So we've actually used more expensive tooling, 1.67 times, and a 67%. We went from 150 tool to a $250 tool, but our cost per part went down. If you look at op 1, which is the periphery of the part at $100 an hour, you can see there 3 versus 5. There's your cost per part machining, and then there's your tooling cost as well. So we're saving almost over $100 a part. So that's a 73% reduction in the cost per part. So we've not only reduced the cycle time, we've reduced the tooling cost and ultimately the cost per part. Again, I apologize. I need to keep uh, my voice going here. The second up on that mold lifter is the top. And again, we're going to start out showing with the 2 flute, 1,000 millimeters a minute, pick feed 1.105. You can see the tool there in the background. And you're going to see the cycle time pop up here in a second for that approach. 28 minutes. So now we're going to go in with the 6 flute, and we've tripled the feed rate. We've maintained the pick feed, but we've tripled the feed weight. We've dropped that down to 10. And now with the barrel tool, we've got twice the feed rate and twice the pick. Notice we're going 0.21 versus 0.105, and we're down to 8 minutes. So that, again, gives you an idea. So to summarize that, we started out here with the 2 flute, 28 minutes. We went to the 6 flute. We dropped that down to 8. We dropped 18 minutes out of that, which is over 64%. But then when we come in there with the barrel tool, we dropped out another 2 minutes or 20% of what was left. So overall, we've dropped that 20 minutes, which is over 71%. So again, a significant reduction in the processing time of the surface of that lifter. So once again, it's the same kind of scenario here. We evaluated it at $50 an hour, $100 an hour, 150, because it's tough for us to know what the shop costs are. But if you pick the $100 an hour, you've taken a part from $50 down to $13. So again, a significant reduction in cycle time, which results in a reduction in cost. Same thing on the tooling. We've used the same numbers. Again, the more advanced tooling, the more expensive. We've also froze the tool life, although we know there are benefits to the advanced tooling. So our cost per part, even though we're buying more expensive tooling, we've dropped our tooling costs from $23, $23.52 a part to $11.12. Oh, once again, we've bought more expensive tooling, but are spending less dollars on each part in tool costs. Excuse me. Again, I apologize. So, in summary, let's look at the second op, which is the top. Machining cost, you can see there at $100 an hour. Tooling costs. So the total cost per part, you're looking at $70 versus $25. So $45 a part. That's a 65% reduction in cycle time in cost per part for the top of the mold lifter. So in summary, we can significantly reduce cutting cycle times. We've removed almost 78% on the first mold lift cut, on 72% on the second mold lifter cut. So it's the side and the top. And we work through those. You can reduce the cost per machine operation. And we showed you there, not only on the first off, but the second off, how you can cut the part from $100 a part to $22 a part on the periphery, $50 a part to $13 a part on the top surface. So you can also reduce the tooling costs, 64% on the periphery and 53% on the top of the part. And were those summaries. Now, the other thing is we've done that. We've had those pretty dramatic reductions in tooling costs, even while purchasing more expensive tooling and not having any consideration for tool life. I mean, we could have went in there just to make this thing really look fantastic and said, hey, we're going to get twice the tool life on the barrel cutter that we get on the, but we didn't do that. You know, instinctively, you know, you're going to get more tool life on both the 6 flute and the barrel cutter. We just don't know what that is. If you could quantify that, this obviously gets much better financially. The total cost per part, again, comparison on the outside of the mold lifter, about 73% reduction in total cost. That's machining and tooling, and about 65% on the top surface. And now, just that's not to mention, you're getting a better part, number one. Excuse me a second. You're getting a better part. You're getting much better surface finishes. So you got less post-process machining operations, which means you can reduce or eliminate your hand finishing. That's going to shorten your lead time. That's going to basically cut your costs. And we saw the numbers we were looking at. 50% would be low compared to what we showed in those examples. If you had just a 50% reduction in machining time at $100 an hour in a year at one shift, 2,000 hours a year, you're looking at $100,000 that you could save in your manufacturing of those parts. Obviously, that's money in the bank, if you will, to your manufacturing operation. And that's based on single shift. That ends the formal presentation. So at this point in time, I'll turn it over to any questions that might, and again, I apologize for the tingle in my throat here.
Thanks, Bill. That was a lot of good information.
You're very welcome. Thank you.
Looks like we have a question in here. And again, you can continue to ask questions in the question panel. It looks like we have a question. What does the work offset look like for a part that is not centered on the trunnion? For example, a part held on a magnetic chuck.
Well, yeah, that's some of the 5-axis technology that goes into the control. And we throw the lingo around TCP. It's called Tool Center Point Control. So if you could picture a chuck, for example, and you purposely put that chuck off center, in the control, there is a measurement that basically tells you, based upon the work offset you put in there, how that chuck moves relative to the center of rotation. All of the dimensions for TCP, Tool Center Point Control, are based upon the center of axis of rotation. So that's how the machine knows if you purposely put that off center, it's going to track that and basically change the move based upon where you put it, how off center it is in the TCP, the tool center point calculation. So, and that's done all automatically by the machine.
And then another question is, what is the material for the honeycomb part?
The honeycomb part was a graphite. It's a Poco graphite. So that's what that material was.
Okay. And then what type of tooling was used on the honeycomb part?
The honeycomb part, the tooling was a traditional cutting surface ball-nosed end mill, and it was made by Voha. Was the manufacturer of that tool.
Okay, thank you. What material was the die mold lifter part?
The lifter part was P20 was the material, and that comes in at a hardness of about 33 Rockwell C HR. So.
Okay. And then what was the harness of the material for the die? Oh, Did I just ask this one?
Yeah, well, I threw that in there. So you ask, and I volunteered. It was about 33 Rockwell C, HRC. So yeah.
Yes. Yeah. Yeah. And then can you share the tooling vendors for the die mold lifter part?
Yeah. Um, the two flute ball nose den mill was actually manufactured by Union Tool. The six flute ball nosed was a Moldino, and so was the circle segment or the barrel tool was also manufactured by Moldino.
Okay. All right. And then looks like we have time for a couple more questions.
Okay.
Can you provide more information on the machine that this was cut on?
Yes. Um, both um, the honeycomb and the lifter part were cut on a Makino D200Z machine. Basically, that machine, if you think about it, is about 300 millimeter faceplate. So you're looking at about 12-inch diameter. Um, it's basically an articulating. We move the workpiece, so you have a B-axis tilt and a C-axis rotary. It's a 30,000 RPM machine. On the honeycomb, we cut a lot of that at 20 and 30,000 RPM. The lifter, obviously, because of the hardness of the material, we still cut that at 12, 15,000 RPM. Some of the finishing cuts were at 20 and 30 on that machine.
Okay. All right. And then maybe give everyone a couple more minutes if they want to chime in with any more questions. But is there anything else you want to add, Bill?
Well, we have both these machines at we have the D200Z both at our Mason facility and at our Auburn Hills, Michigan facility. So we have the ability to work with you and, maybe get your part cut on one of those two showroom machines.
Okay. I think that's it for questions.
Okay.
But that being said, for those listening, if you'd like more information, you can feel free to contact Bill or Makino at the contact information on your screen. I'd also like to thank the organizers for helping the webinar run so smoothly. And most importantly, I want to thank all of you for listening in. We just got a last minute question. Do you offer any training?
Yes, we do. We offer a wide variety of training. We recognize that in order to make the optimum use of the machine and in order to get the best results in your workpiece, there's all kinds of training that relative to what tooling works best on what materials and programming and fixturing and tool path, all of that. So we actually have what we call a die mold training class that we offer. It's typically at Auburn Hills, Michigan. It's about a 4-day long, and it goes into all of the factors that you would need to think about as you employ one of these machines into your manufacturing process. Yes.
Okay. And
that comes free with the machine as part of the machine purchase. So yes.
And then we also have, is there anyone who I can discuss my part with?
We have application staff. The die mold is primarily based out of Auburn Hills, but yes, we have folks on staff and literally, we have the folks there, we have their offices, we have a number of programming systems to support that and you, and then we have a showroom with quite a number of machines on the floor that we can literally go out and do test cuts and parts. You can either come in and see that, or we have what we call experience centers, which are high-tech centers, both at Mason. We actually have 2 at Mason in Ohio and 2 at Auburn Hills, where we could literally have a real-time telecommunications meeting with you. We can go out and show you the equipment on the floor. And we literally have cameras on the machines. We can share, the showing you the machines cutting. So we can set that up and have proprietary confidential meetings with customers. Yes.
Okay, awesome. Well, that does look like the end of questions now, I think, unless anybody wants to chime in. Um, but again, I'd like to thank the organizers and you, Bill, for helping the webinar run so smoothly. And most importantly, I want to thank all of you for listening again, for listening in. And again, if you have any additional questions, anything you think of later, you can contact Bill at his email listed. And this is recorded, so you can watch it online later as well, along with our other webinars on moldmakingtechnology.com. And this concludes our webinar. Have a great day, everybody.
Thank you.